Good afternoon, I'm Sarah Badawi.
I'm Shining Gao.
I'm Rajan Basoya.
My name is Megan Yip. I'm Jin Yu, and our research is on the chemical dissolution of soda-lime Silicate glass for safe drinking applications. We would like to begin our presentation with a brief overview of what we will be discussing today. Starting with our objective. Our objective is to create a more cost-effective glass for safe drinking applications. Then we will move on to the background of our research, the steps we took in our research, and then the conclusions and the data results we were able to get. Finally, we will discuss the future work that we hope to see accomplished. In order to create a cost-effective glass, it is very important that the glass is not only safe and durable and for usage, but also that it is very cost-effective to produce. And so we are trying to modify the current standard industry glass composition in order to make it have the properties that we want. The cost effectiveness of a glass is actually dependent on the melting temperature at which it is created on. So by lowering the melting temperature of the glass, we are actually decreasing the amount of energy that is required to create this glass, and thus the overall cost production of our glass. We decrease the amount of silicon dioxide in our glass because it has a very high melting temperature, and increase the amount of sodium oxide, which has a very low melting temperature. However, silicon dioxide actually has a very strong property, and so by decreasing the amount of silicon dioxide, we were decreasing the overall durability of our glass structure. And so, to make up for this lack of durability, we increased the amount of boron oxide and calcium oxide.
We relied on several important processes to create our glass. As Ginny mentioned, we want our glass to be cost efficient. This means we want to spend as little amount of money as possible on the materials. Three important components of our glass are calcium oxide, sodium oxide, and boron oxide. However, these are expensive compared to calcium carbonate, sodium carbonate, and boric acid. Thus, we calcine the cheaper materials to get the desired ones. Calcination is the process of heating materials to very high temperatures in order to remove volatile substances. By calcining the cheaper materials, we're able to get the desired materials and save more money. Now, glass is an amorphous structure, which means that the atoms are randomly arranged as opposed to a crystalline structure in which the atoms form a patterned network. If we want to create our glass so that the atoms are randomly arranged, we must cool it very, very quickly to ensure that the atoms don't have time to arrange themselves. This process is called quenching. Now, quenching results in internal stresses within the glass that must be relieved. Thus, we anneal the glass, which is the process of very slowly cooling the glass to relieve the internal stresses.
So when preparing for the dissolution of our glass, we wanted to simulate multiple environments that our glass might be exposed to. So we chose 3 beverages with varying pHs: Pepsi Cola, Arizona iced tea, and tap water, with Pepsi Cola being the lowest on the pH scale, being the most acidic, and having tap water being around the neutral area of the pH scale. Now, when analyzing dissolution, this gives us information on 2 important characteristics of glass: its chemical durability and its safety. If a glass were to be dissolved in a beverage, that wouldn't be safe because glass would be consumed. And also that would mean that the glass is not chemically durable because it chemically reacted with the beverages that it was holding. So in order to measure these 2 characteristics, we will perform FTIR analysis and analyze the mass lost.
FTIR stands for Fourier Transform Infrared Spectroscopy. What it essentially does is it takes an infrared beam and shoots it at a sample. Now, depending upon the bonds within the sample, the wavelengths of that beam will either be absorbed or transmitted right back. Now, we can identify, depending upon what was absorbed, the specific bonds within our material. So, our glass is composed of silicon-oxygen bonds. So we can determine the concentration of silicon-oxygen bonds comparatively between each of the samples in our next test.
As stated previously, we wanted to reduce the total cost of producing our glass. Therefore, we reduced the amount of silicon dioxide, which has a high melting point. By doing this, we reduced the melting point of the glass and therefore utilized less energy to produce the glass. At first, we were presented with molar percentages, which we then converted into mass percentages. And with these mass percentages, we were able to determine the relative amounts of each ingredient in grams. Then, we took these ingredients, which existed in a powdered form, and combined them together in a mortar and pestle. Then, we calcined the ingredients within a machine. However, the calcium carbonate had to be calcined separately because calcium carbonate has a high calcination temperature compared to the melting temperature of sodium. Then, after the glass was calcined, we took the 2 calcined mixtures together and we melted them within a furnace.
Once the mixture was melted into a molten state, we took this molten glass and placed it on a metal slab and completed the process of quenching. And by doing this, the glass cooled at a quick rate to about 600 degrees Celsius. To prevent the glass from crushing under its own pressure, we then placed the glass within an annealing furnace, which slowed the rate of cooling within the glass. Once we were left with our finished product, we placed this glass within a mortar and pestle once again and crushed it into a fine powder of sizes roughly ranging from 300 to 425 micrometers. And with this fine powder, we were able to complete the dissolution process at a much exaggerated rate.
So as Megan said, after the crushing of the glass, we actually performed the dissolution experiment. Now, to do this, we prepared two 500 milliliter samples of each beverage, giving us 6 samples in total. Now, one set of these samples acts as our control group. This is to account for the natural changes in pH over time of our beverages if we were to leave them sitting out. The other set will be our experimental group, in which we put 2 grams of the parent glass into each container, and we monitored the pH for 138 hours. Now, when monitoring the pH, we made sure we took our readings on the hour, just to ensure that we had even time intervals in our data. Next, we had to analyze the mass loss, and in order to do that, we had to filtrate our glass out of the liquids that they were being held in. So to do this, we took a syringe and took off most of the liquid off the top of the glass, and we poured it into a funnel and filter paper structure just to ensure that we didn't lose any of the glass that might have been sucked up in the syringe. Now, when there was a small amount of liquid left in each container, we put these in an oven to evaporate the remainder of the liquid to leave us a dry glass, which then we could put under FTIR analysis and compare to the parent glass later.
These are the results we collected for the pH values. As you can see from the tables, there was a basic trend in the experimental data with the beverages that had the glass. And so this means that the numbers increased in the pH values. In comparison, the control group actually saw, with the exception of tap water, a more acidic change in pH, which means that the pH values decreased in number. However, overall, we saw that there was negligible pH change, which means there was an insignificant change in the pH values because all of the changes occurred within its first term. In addition, it is important to note that Pepsi Cola actually has a buffer called fumaric acid, which could have accounted for maybe why the Pepsi Cola did not have as much pH change in comparison to tap water.
As Shining stated, we poured 2 grams of glass into our 3 beverages. After 138 hours, we measured how much of that glass was left. It was found that in tap water, the least amount of glass dissolved into the beverage, with only a 4% decrease in glass mass. Next came Arizona iced tea with a 4.5% decrease in glass mass. The most glass dissolved in the Pepsi with a 6.5 decrease in glass mass. It's because these are all below 10%, we could say that the mass loss was negligible. Also, it's important to note that the surface area to volume ratio was very high because the glass was crushed into a very fine powder. In the industry, however, the glass would be molded into a container, and the surface area to volume ratio would be much lower, and we would expect the mass loss to be lower as well.
These were the results that we got from our spectrometer. What we can see here is a graph, and what we're looking for are peaks in this graph, which we can identify bonds from our material with. Now we're looking for variation in these peaks. So the main difference is in the right side of the graph. We can see here what bonds of our glass are specifically represented, and using the black line and the purple line, which are silicon oxygen and aluminum oxygen respectively, we can see that there's a huge variation, but it's very important to note that the mass loss was extremely small. Also, these two substances, aluminum oxide and silicon oxide, are glass formers. What that means is that they compose the structure of our container glass. So in order to really see their effects, we have to test with the container glass and then see the structure of the container glass. But the rest of them are not exactly, they aren't glass formers, and therefore they don't compose the structure of it.
Overall, we were able to meet our objective. We were able to lower the melting temperature from 1,675 degrees Celsius to 1,500 degrees Celsius and thus make a more cost-efficient glass. Also, our glass is more durable because both the mass loss and pH changes were negligible.
With our experiment, we were able to determine that there is potential to create a more durable and cost-effective glass. We can do this by altering the industry standard glass compositions to fit what we want in our glass properties.
In terms of future goals, our research can be expanded in 2 ways. First, the glass can be tested in order to determine exactly how much energy is conserved by lowering its melting temperature. In addition, durability testing can also be conducted. However, we were unable to complete this test because of our 4-week time limit. Next, we'd like to thank a few very important people. First, we'd like to thank our project mentor, Edmund Hahn, for guiding us through this entire process and ensuring its success. Next, we would like to thank Dr. Eileen Rosen, along with Associate Director Jean-Patrick Antoine, for giving us this important opportunity to pursue such high-level research. Finally, we'd like to thank a few of our sponsors who funded this program and also allowed us to conduct this research, namely Rutgers, the State University of New Jersey, Rutgers School of Engineering, the State of New Jersey, Silverline Windows and Doors, Lockheed Martin, South Jersey Industries Incorporated, Novo Nordisk Pharmaceuticals Incorporated, and New Jersey Resources. Thank you for your time.
Does anyone have any questions? Yes.
You mentioned that the dissolution of the glass, the mass loss was under 10% for your experiment. What's the industry standard for mass loss?
So it's very important to note that we use powdered glass because that exaggerates our results. Now, in using powdered glass, no other industry standard uses that because they have a very long amount of time to test their product in the container form. So ours was exaggerated. Using that, we know that the surface area to volume is extremely high, therefore it's extremely exaggerated. 10% is a very large number, I can concede that. But the thing is, it is powdered, so it's going to be exaggerated. It's going to be extremely large.
Go ahead.
Can you clarify why you can reduce melting temperature of the glass so that it saves cost? And secondly, can you quantify that? For every 100 degree increase in melting point, how much dollars and cents you save on per unit square inch of glass? Your estimate?
Actually, for the second question, that was actually something we were going to be talking about for future work. We hope to see that we can actually measure exactly how much money we'll save or how much energy we'll save. But going back to the first question, by lowering the melting temperature of the glass, we're actually lowering the amount of energy that is required to create the glass, and thus this is overall lowering the amount of cost it needs to produce this glass. So that's why.
Go ahead.
How would you present this to industry for the current glass makers to mass produce your type of glass, considering that when you replace the chemical that had the high melting temperature, you replace it with, I think, barium oxide and more expensive materials that you then have to do a separate step to extract from, like with a separate chemical process, which wouldn't be, I mean, I'm assuming not as financially conservative, although it is definitely way more energy conservative. How would you tell companies to proceed with your experiment?
So the extra step is calcination, which requires high temperatures. So when we're melting our material, we can just put it all in. So we're using calcium carbonate, we're using sodium carbonate, and we're using boric acid, which aren't the boron oxide, calcium oxide, etc. What we're doing is we're literally putting it right into the batch and just putting it in and melting it. And what that does is it releases the volatile substances already within it. So there is no extra step per se. We just have to heat it up and it will do it on its own because the volatile substances are volatile. They'll be gases and they'll be removed from our batch.
And this is all during the melting of the glass to form the powders together to make that molten state of the glass, to cool it and make the actual glass itself. Yes, in the back?
Just when you talked about the calcination process, right, it produces CO2.
Mm-hmm.
So how would you just envision in an industrial environment where you're producing more carbon dioxide, we want to reduce, right, overall, how do you envision that increased production of CO2 offsetting the cost benefit?
So calcium carbonate, when it's released, so what's already used is calcium carbonate because it's extremely cheap, right? So compared to calcium oxide, it's extremely cheap. And the way that's produced is the same exact process. What we're doing is putting our own energy input and basically cutting out the middleman in that process. So the CO2 would be produced either from someone else and we then buy calcium oxide, or we would do it ourselves and us save money. All right. Any other questions? Thank you.
Thank you.